I'm going to go ahead and work out some of the problems from 4.1, which are having to do with linear functions. And on this video, I think we'll do two problems. One will be, this first one is going to be like problem 17 and the surrounding problems in section 4.1 in the book. So let's just go ahead and answer these questions here. And they give us a function. It's f of x is equal to 1/2 x minus 5. And they're going to ask us first to find the slope. Well, in general, this equation is in y equals mx plus b order. And when that is the case, the slope is the value in front of x. So our slope here is 1/2. And the y-intercept is the constant, because when x is 0 on a graph, we end on the y-axis. We end up having a point on the y-axis. So when x is 0 here, we would have -5. So our y-intercept is 0, -5. Okay, it says use those two pieces of information to go ahead and do a graph here. So let's give this a try. We're going to go ahead and start at the y-intercept of 0, -5, and that would put us right here. And then we're going to go ahead and count off a slope of 1 to 2, which would put us up 1 and over 2, and up 1 and over 2, and we'd get a general idea of how the graph is going to be, something like this roughly. And the next question then is we're to go ahead and determine what the average rate of change is. Well, they're introducing language that really means the same thing as the slope. It's just that on some non-linear functions, we would have a curve of some kind, and the average rate of change would not be constant. We couldn't say that the slope of a curved line is just, for example, here, if I had something like this, we can't say that the slope is 5 or 2 or 2 over 3, because it might be an average rate of change here but will be different than the average rate of change here. Now we could calculate the average rate of change within certain segments of the function and say that on the average it was a certain rate of change, but we couldn't say the rate of change across the whole function was the same like we can with a linear function. The linear function has a constant rate of change all throughout the function. So for us, on this problem, the average rate of change is 1/2, 1 to 2, up 1 and over 2. Okay, well, as far as that average rate of change being an increasing, decreasing, or constant rate of change, that is determined by looking at the slope, at the line itself. If it's rising, then the function must be increasing. If it was falling, the function would have been decreasing. So in our particular case, it was an increasing situation. The function is an increasing function. Excuse me. So let's just go ahead and take a look here at the next problem. And this problem would be similar to problem 21 and the surrounding problems in the book. Here is a chart of ordered pairs, and they want us to determine whether this is a linear relationship or not in this function. Well, this really relates to the conversation we just had on the last problem, because if this rate of change, the change of y over the change of x, if it turns out to be constant from point to point, then we do have a linear function. If not, we'd have some kind of curve like we drew up here as an example of a nonlinear function. And so in this case, the change in y here, 3 minus 8 is -5, while the change in x, 0 minus 1 would be -1. We'd have a -5 to 1 slope, or a -5 to -1 slope, which would be 5. And that would be a situation that would give us just the slope between those 2 points, but we got to go ahead and see if that is remaining to be true on the other points. So let's see what happens here. This would be 8 minus 13, that's -5. And 1 minus 2, that's -1. And from 13 to 18, that's -5. And this 2 minus 3 is -1. And 18 minus 23 is -5. And this is -1. It looks like our rate of change is constant, and therefore this is a linear function. And here's where we're going to say yes. Then it asked us about the slope of the function. Well, it turns out all throughout that function, the slope was -5 to -1, or simply 5. And this was the slope of a linear function. And that's the end of that problem.